Good morning, everyone. It's great to see you all here on day 2 of Øredev. It's very exciting to be part of this. My name's Nash. I'm a developer advocate from a company called Sonar. Sonar is the home of things like SonarQube and SonarCloud and SonarLint, which are all different tools that help you check your code quality, lint your code, and check that code quality and health over time. I'm going to talk a little bit more about them later as I use them for the data. But first, let's talk a bit about myself. I am excited to be here because I'm over from Melbourne, Australia, which means I still don't know what time it is. I guess it's the morning, but I've been awake for hours already because it is nighttime at home and I don't know what's happening. Very excited to carry on. If you ever want to find me, I'm Phil Nash, all over the internet, happy to answer questions and about this, about Sonar, about anything you might ever want to know about. But today I want to talk about the top 5 issues in all of our JavaScript code bases. And I need to lead with kind of what do I mean by that? Because it turns out I had some data about this. And so SonarCloud is a SaaS solution which allows you to scan your code bases across many languages. I'm mostly interested in JavaScript and TypeScript, though. And so what I did was dig into the data inside of SonarCloud, which was hundreds of millions of lines of JavaScript and TypeScript, and pull out all of the issues that are raised in each of those projects across those hundreds of millions of lines. It's kind of exciting. I thought it was kind of cool. These issues, of course, are static analysis issues. So SonarCloud does static analysis on your applications to try and find bugs and issues and things that are wrong, code smells with your code bases before you push them to production, before you get them out into the world. And so those are the kind of issues we're looking at, and that's the kind of data we're pulling from here to find out what these are. Now, quite interestingly enough, of course, the most common issues then tend to be things you've probably heard of. And so I've got 5 of them, but I'll be counting them down in different orders because I think the most exciting ones are somewhere in the middle. We'll see about that later, though. These JavaScript issues are really about issues in our code that we can fix before we run it, before we push it to production, before we do anything with that. And what we're really talking about, what I'm really kind of trying to talk about, is the idea of writing clean code that is both great to work with in development because it is readable, it's understandable, it feels maintainable, but code that then works well in production as well. It's free from bugs, free from software vulnerabilities or security issues. And free from, bugs mostly. That's what I'm trying to avoid. So I'd like to start with a couple of quotes on this particular one. It's one of my favorite ones about kind of coding. Always code as if the guy who ends up maintaining your code will be a violent psychopath who knows where you live. Code for readability. This is a quote from John F. Woods. He's a C++ games programmer. This was on a C++ mailing list back in 1991. It's very good to know that people cared about code quality in C++ in 1991 to the point that they would threaten violent psychopaths. I thought this was interesting, though, because it was on a mailing list. These are publishable and searchable these days. And so I went back to find out what the topic was about. And it was actually a discussion about the comma operator in C++. And I thought it was kind of funny because this code would parse as JavaScript as well. The discussion was about whether people should recommend using the comma operator so that you could do multiple things on a single line, and then you could avoid having parenthesis around the condition, around the code that runs after the condition. And that's a bad idea. This is kind of hard to, getting rid of brackets is not a good way to make things more readable or more understandable. And doing so with the comma operator, one of the smallest operators we have available to us, is a nightmare. And I'm pretty sure that anybody who's written JavaScript at any time in their life has found themselves searching for, a missing semicolon or a semicolon that should be in the right place. And if you typoed the comma to a semicolon, it shows up on this slide because there's syntax highlighting in it. But in 1991, I don't know what they were doing. But this changes the meaning of the code immediately because there's a tiny extra dot. And so it makes it much harder to read. And that was ultimately, thankfully, the outcome of that outcome of that discussion on the C++ mailing list was that the comma rate is a bad idea. Let's do things on multiple lines. Let's leave the brackets in because that is more readable, and you don't have to find yourself searching to find the tiniest of operators to see if it's in the right place or not. And so it's silly little things like that that can actually make a big difference in your code and how you read and understand your code bases and how you work with them. I've got another quote from Raymond Chen on a Microsoft blog that says design for readability. Now, John F. Wood said code for readability, and this now says design for readability. Because even if you don't intend anybody else to read your code, there's still a very good chance that someone will have to stare at that code and figure out what it does, and that person is probably going to be you 12 months from now. Now, that's normally pretty good. If it turns out you're also a violent psychopath, you definitely also know where you live. And so you've got to keep that in mind too, just in case. But coding, like designing for this readability, this is the idea that code itself is read many more times than it's written. And code is written so that we as people can understand, we as humans can understand it and know what's going on. Not so that a computer can run it, although that is a nice side effect of our code. If we were writing code just so a computer could run it, we'd still write assembly. Instead, we want to be able to share our ideas and work with other people and maybe even ourselves in the future or our past selves in order to achieve an outcome with our software. Achieve the sort of value in our software that we talked about in yesterday's keynote. So that's what I'm talking about in terms of clean code. I'm talking about code that is worthwhile reading, understanding, and being able to maintain, as well as then running well when we deploy it to production. And so let's get into our top 5 issues. Like I said, I dug these out from existing projects. And like I said, they are also things you've probably heard of. So we'll count down backwards to start with. We'll start with the top 5, with number 5. And just to add some extra excitement, I threw some confetti on the screen when we get them. So, woo. So number 5, not bad, right? Unused assignments. This one was a funny one. I wasn't expecting this to be an issue, but it turns out there's quite a lot of JavaScript out there in the world that does something like this, where you assign a variable to something, and then you reassign it sometime later without having done anything with the thing in the middle. This is very easy to spot when you only have 2 lines of code on the page. But if this is the top and bottom of a function where nothing happens to happen to the foo variable in the middle, it's quite a lot harder to spot. And so this actually, confuses what we're doing in this function. If we are doing something with a variable and then it never gets used, why do we do that thing in the first place? Was the outcome of assigning it in the first place what we really wanted, or was that completely useless? This is, like I said, it's an easy thing to spot when they're next to each other. It's much harder to spot if there's different parts of, if it's got several lines of code in between. And so tooling normally helps point that kind of thing out to you. And indeed, that's what Sonar Cloud would be doing in this case. One thing I thought was interesting about this, and one kind of way this turned out, was actually in functions like this, normally more complicated than this. But what they did was, what I found was in a bunch of open source projects, funnily enough, that a function would not only return the result, but also assign it to a variable in a higher scope. And this is kind of the epitome of like side effect-ridden code. If you have a function that is simple enough that it will return the same thing each time, it really shouldn't be affecting something somewhere else in the state of the application. And the fact that it does that is confusing and is hard to understand what the actual implication of running this function is. It should be simple, but it's not because it's doing some external assignment. So this assignment is not necessarily unused. It's unused in the context of this function itself, but it is making something happen somewhere else that we don't necessarily know about. So I dislike that quite a lot, and it seemed oddly popular. So I'd say avoid this kind of thing. Avoid mutating state in your application inside a function that could be pure and side effect free. So that's unused assignments. Let's drop those. This is good. Next up, who's a big fan of using double equals for equality? No one. I've given this talk before and people have put their hands up. They're like, yep, love double equals. Don't know why. It's horrifying. It's horrifying because of this beautiful graph, which you may have seen before. This is the equivalence chart of double equals against a whole bunch of different things. Now you can see down the middle line, this is where things are indeed the same thing. And then all the other green blocks are things where we've coerced one into another and it turns out to be equal. This is the epitome of all bad JavaScript interviews, where you're given, I don't know, the string 1 and the number 1, and you're like, is that equivalent? Yes, yes it is. Good. But like, what about true and an array with a single element in it that's a number 1? That is also true, it's at the top there. But why? I'd rather not know. I'd rather not know. And so avoiding this kind of thing is very nice. Very easy, because if we avoid coercing things, we get the very simple graph using triple equals. And obviously the equivalence for double not equals as well. Some people, so when asking people about why they might like double equals, they say things like you can use it to get equivalence of null and undefined at the same time. And I say, why not use triple equals null and triple equals undefined? It gives you much more, it communicates more about what we're actually trying to do with a piece of code. Not only that, but actually, if it's a particularly hot loop of code that you might be doing an equality check in, and you're using double equals against things that need to be coerced into different objects in order to be compared, it turns out that's about 100 times slower than just using triple equals. So if it's it's a pretty fast thing, but if it's a very hot loop and performance is top of your mind, then coercion with double equals is also a bad thing. So that's a nice and easy one. I think we can all agree that we can just drop double equals, forget it even existed. Cool. In at number 3, sections of code commented out. So this is another readability issue. I don't even have an example for this. It's just sections of code shouldn't be commented out. If you're committing commented out pieces of code into your repository, I don't know why. Like, what my problem with this is if I'm reading a function and it has a piece of commented out code in it, then my brain has immediately forked and gone, okay, I need to understand what this function is doing with the non-commented out, but I also need to know what the commented out code is, why it's there, and should it be coming back at some point? What is the reason for this to exist? And the thing about checking in commented out code like that is simply that we don't, if it's code that did exist and maybe will come back at some point, that's what our version control system is for. We really should, some nods, I like that. Agreement that Git is on our side here and not code comments. Comments should be there to document code and explain things as they're going on, not add extra code that doesn't actually run. So that's a fairly straightforward one. So I thought I'd take a TypeScript break for this. Because those are actually, like this top 5 we're looking at is actually from JavaScript projects, and I was kind of interested to see if we had different or same things in TypeScript projects. And they are slightly different. It turned out that sections of code commented out is the number 2 issue across TypeScript projects that can be fixed nice and easily as well. Just delete them, it's fine. But TypeScript, I'll run through these a bit quicker because JavaScript's my thing. In at number 5 for TypeScript was the use of to-do tags, another commenting thing, which I think is good. Actually, so I had a colleague recently who looked at this list for the same thing in Java, and a lot of the things actually turn out the same. But he was writing about this and how to fix things. He was just like, well, just do the thing. I'm like, that's fine. But if you actually turns out you've got 100 to-do comments and you just found out about them, you probably don't have the time to just do all 100 of them right now. To-do things seem to be, to-do tags tend to be something that you haven't implemented for some reason and you need to come back to. All I'd say for this is it's much better to tag these things as actual tickets in your system so you can prioritize them effectively as part of your sprint or however you like to work, rather than just leaving little notes to yourself in code. Whilst to-do tags like this would still cause an issue in something like Sonar, I was talking to somebody just 2 weeks ago, who said they have a rule in their code that they can have a to-do as long as it also has a link to a bug in Jira in that particular case. And that's fine. I think you need to be able to store these things somewhere else, not just in the code base. So that's happening in TypeScript, apparently. In number 4 was actually a React thing, which I think is very cool to see that there are React problems in all of this. And this is a quick one on using bind or arrow functions in JSX props. The issue with this is that it could be a potential performance issue in the future. It's something that React documentation used to say, don't worry about this. But I always like to think that if something's a potential issue in the future, I'd rather not find out about it when I've done it 100 times and need to fix all of them. I'd rather just have the thing done in the first place. And so this is a class-based component because I'm old school apparently, but the idea is not binding in the JSX there, but instead binding it beforehand. Or creating an arrow function outside of the JSX so that each time it renders, it doesn't need to be rebound and add more things going on in your application. Up the top in TypeScript as unnecessary imports. Just doing a thing, importing a thing, and never using it. Now, I'm so surprised that this turns up as like the biggest issue, or the most common issue in TypeScript projects, because I know that all my tooling kind of complains about this, has things faded out when it's never used, and it's easy to remove things. On the other hand, of course, you can argue that this doesn't actually do anything, and in a TypeScript project, if you import something and never use it, it gets just stripped away by the compiler, which is great. But it's just, to me, another readability issue, another maintainability issue. Every time there's an import in a piece of code that doesn't get used, my question is, why is it there? Was it thinking about being used? Did somebody previously use it and stop using it, or were they going to use it and never got round to it? And that's stopped me reading and understanding the rest of the code. So just dropping these things, nice and easy. So I left one space in TypeScript there, in at number 3. I've left 2 spaces in JavaScript, number 2 and number 1. I'm going to go for number 1 next. And does anybody have a guess as what the most common issue that you can find with static analysis in a JavaScript project might be? Any guesses at all? Leaving console logs in. That's a good guess. I've not heard that one before. It's not, thankfully. But it's a good guess. Any others? Using the eval function. I'd hate to think that we were all just littering our code bases with eval enough that it would come up top all the time. No, it is our favorite new feature from ES 2015, ES6, which is a good 8 years old now, and that is using var instead of const or let. Look, I know it's not a big issue. It's declaring a variable. It's probably not going to break your code. But again, all I'm trying to get across here is that actually the benefits we can get out of fixing even seemingly trivial issues like this are understandability and maintainability. Because var tells you that this function can maybe be reused, can maybe not. It can be used above itself or below itself. It can be used in some kind of set of scopes. But let or const communicate a bit more than that. Const tells everybody else reading this that we don't intend to change this assignment. And let says we probably do intend to change this. And if it turns out a let described variable is not changed later, then there's a question to be asked as to why, and can we change that and fix it for the future? We also know that, const is sort of constant. It's constant assignment, not necessarily constant objects inside of that. But this does allow us to just communicate more and take advantage of the block scoping of these elements as well. I'm not also telling everybody to go home right now and search through your code bases to find every instance of var. It's probably not going to be an issue for you right now. But as you work through your code base, if you find these kind of things, then you can kind of update stuff as it happens, as you work on it, in order to communicate more about the code and leave your code base better every time you leave a file and check something in. And so that's 4 of the top 5. And for most of these, like I said, they're relatively trivial things that we could fix and make things better. And that's why I was excited about number 2, and indeed it was number 3 in TypeScript. It's the same project, same issue. And that issue is that the cognitive complexity of our functions is too high. And I added extra confetti to this one. Maybe too much. Because yeah, it was TypeScript as well. Cognitive complexity of functions is too high. Has anybody here heard of the idea of cognitive complexity before? There's a few, right. And has anybody heard of cyclomatic complexity? There's also a few, okay, like the same kind of people. And you might think they were the same thing. But cognitive complexity is a measure of the complexity of the maintainability of a function. And I like to, like cyclomatic complexity is something that's been around a lot longer, so I like to compare it against that. So cyclomatic complexity is a score for a function based on the number of routes that you can take through a function in order to, the number of routes you can take through a function. It's effectively a count of the number of unit tests you'd need in order to completely cover that function. And it's calculated by this. I've got this example function here, which is a sum of primes. So you give a number and it will sum up all the prime numbers underneath that number. Not the most useful function for a web application or something like that, but hey, it's a good example for this. And cyclomatic complexity says, hey, we start with a score of 1 because a function needs at least 1 go through it in order to find out if it did anything. And then every time we do a for loop, we also add 1. Every time we do a conditional, we also add 1. And so this function itself scores 5 in terms of cyclomatic complexity. You need to write 5, don't restart. That's exciting. We'll see if it does. Cool. I've got 60 seconds, let's go. Cyclomatic complexity counts that number of routes through it, and we've got 5 routes through this function. Funnily enough, I have a second function for you, which also scores 5 in cyclomatic complexity. It's this one. This is a number that gives you a number of words if you give a number to it. So if the number's 1, it comes up with the word 1. If it's 2, it's a couple. If it's 3, a few. If it's 4, many. If it's 5 or more, lots. And so because this is a switch and because each one has a different route through it, we score 1 for it being a function and then 4 for each of the cases. And this gives us 5. And you probably agree, I'd like to think you agree with me, that this function with its 2 loops and nested conditionals is not the same complexity when reading it, when trying to understand what's going on, as this switch statement. And so cyclomatic complexity is useful as a figure because, it, as I said, it tells you how many unit tests you need to fully cover this. But I don't think it tells you enough about maintainability, about how to understand the code that you're writing. And so cognitive complexity, so cyclomatic complexity measures the routes through the function, paths through a function. Cognitive complexity intends to measure how easy it is to read a function, to understand it and to maintain, and to be able to work with it. This was come up in this. We came up with. There were people at Sonar who came up with this in 2016, and it's still a score similar to cyclomatic complexity, but we've tweaked the way it works. The cognitive complexity itself actually creates a score by incrementing for breaks in flow, so loops and conditionals, as we saw in cyclomatic complexity, but also it increments a nesting score every time you nest further in, and that score is added at the same time as each kind of break in flow. And so I can show you that in our example functions again. So our sum of primes here, we don't score for being a function, because I don't see the point in that. But what we get is our first for loop scores 1. But then we are now incrementing. We're inside the loop, so the nesting score in the background is also now 1. And so our second for loop scores 1 for being a loop, plus 1 for being nested once. Then we're inside 2 loops, so our nesting score is 2, and the if statement, our conditional here, scores 3, 1 for being an if statement, 2 for being nested twice in. We don't have anything inside that if statement. We then drop out the loop, so the nesting score decrements back to 1, and so this conditional then scores 1 for being conditional, 1 for being nested once, and we end up with this score of 8. Meanwhile, our getWords function has a single conditional in it. A switch statement scores 1 because it is understandable. It works with 1 variable, and we just check a bunch of different conditions against it. And so our getWords scores 1, and our sum of primes scores 8. And that understandability, the idea that 2 loops, 2 nested conditionals is more hard to understand than a switch statement, definitely makes sense to me. And so the issue that's brought up in our scanning is that the cognitive complexity of functions is too high. To be too high, we need a threshold for that. And the threshold that is set at least in Sonar, is 15. And so I want to kind of show you a bit of an example of that and see what we actually mean by this, because thresholds can kind of seem arbitrary. The number 15 could be plucked out of anywhere. But what I think is important for this is how we use the fact that we have breached kind of a conditional like that, breached a threshold like that. And so as I was writing this talk and I wanted to put confetti on my slides, I had to write myself a plugin to actually do the confetti. So I'm using Reveal.js. It's a JavaScript-based set of slides. This is all in a browser. And then I wrote a bad function to do the confetti. So on the end of a slide transition, we get to trigger some stuff. And this is a particularly long, it's almost 80-line long function that gets run at the end of a slide transition, which is cool. There is a large kind of options block in the middle, so we can sort of ignore that, but it's still quite just a long function. And as you can see, there's a bunch of kind of ternary operators here, so conditionals that don't necessarily nest. We've got nested conditionals. We've got a whole big nested conditional around the outside. And I'm running VS Code here, and I've got SonarLint, which is our free extension which does linting for you as you're writing it. And it's pointing out that this function has a complexity of 16. So it's definitely breached our 15. And what we can actually do, which is quite nice, is tell us where all of those locations are for where we've scoring points in this function. And so you can see I've got this one big conditional around the outside, which is only scoring 1, but it is increasing the nesting for everything else inside it. And so this ternary scores 2 because it's 1 for nesting. That's 2 for nesting. We're going to add we nest more, although that doesn't have a problem. This ternary is scoring 3 for being nested twice. And so when you breach a threshold like this, I think it's a really good indication that this function is ready to be refactored. It's ready to be turned into something that we can that's easy to understand again. And obviously there are a lot of concerns that have been kind of modeled up inside of this function. But I want to say, like, we're not just aiming for 15. Like, if you get to 15, we're not happy again, because I could do that. I can write a function that does what have we got here? I'm getting a particle count. So we look at the current slide and we check its data attribute confetti particle count, and we try and parse out an integer from that or make it 200 by default. And so if I get integer data attribute integer or default, I can, there we go. CodePilot is here to help. That'll do, although we'll use that's 10. Yep, cool. So if I do that and then replace this particle count here by just going, by using my data attribute integer default and handing in the current slide and the attribute, which is confetti colors count, and make that 200 because that was the original answer. Then what we do is we remove one of those ternary operators, and actually we've made the thing happy. It's now 15. It's not breached the thing, but obviously I've just moved a bunch of stuff to one function, and the whole thing is just as confusing as it was in the first place. The idea to me that if we breach this cognitive complexity threshold, what we can actually do, what we need to do is actually look at the whole thing itself and fix it entirely. And so I'm not going to spend the rest of the time writing a bunch of stuff, but like pulling out those those data attribute things. This one gets an integer, this one gets an array of stuff. Pulling out a function for each of the confetti types from our medium, small, and large. And then the on-slide transition end function then becomes much more easy to understand. We also drop out that entire big conditional around the lot, so we stop nesting everything so badly. Now has a different issue there, but which I can fix later. It's cool. But like, this is much more understandable now. We get some default stuff. We get an array of colors. We get a particle count out of here, and then if we have some things, we call on small, large, or medium confetti. Job done. Much easier to understand. And now we have a cognitive complexity of, what do we got? 1. Those are all fine. 2. 3. It's now a cognitive complexity of 3. So much easier to understand and much easier to reuse parts of this as well if we ever want to. So that's cognitive complexity. It turns out we're writing functions in our JavaScript that are just too hard to understand. It's a bit of a shame, but it's something we can fix if we're aware of it. And I want to go into one other part about this. Like, complexity is inherent in the work that we do. I'm not saying that every function can be done in 3 lines of code. We do need to be able to do complex things, but it's the accidental complexity that we add as we build and change things over time that can lead to breaching a threshold like this. Once we find that we've done that, that is why it is a good time to take a step back, reconsider, refactor before we then move on. And if you don't, if you know that a function is behaving like this, then you can try and take it apart and work on refactoring it so that it is easier for the next person to understand, whether that's your colleague, whether that's you in 12 months' time, or indeed whether it's a violent psychopath who knows where you live. And so those are the top 5 issues in JavaScript. Mostly easy things to deal with. Aside from, I think, this cognitive complexity, I think there's a lot more to deal with in terms of refactoring those things. And I intend to write about that more as we go on for next year. It's straightforward, I think, to if you can find those unused assignments, we can get rid of them. If you're using double equals, there's some questions to be answered there. If you have sections of code commented out, you can simply remove them. They will exist in your version control. If the cognitive complexity of functions you find too high, if we have excess complexity in our work, then we can work on that and refactor to do things better. And finally, we'll fix those files. It's fine. If you see them in your code, you can decide whether you want to make a change at that point. And indeed, that I think is an important thing to consider as well. Like, if your application is running smoothly right now, then you don't necessarily need to change these things for no reason. It's just as you work through and find these things, you can change them and make them better for the future. And so these are some tools that you can use to find some of these issues. As I said, I got the data from Sonar Cloud. It is free to run open source versions of open source code through Sonar Cloud. Or Sonar Cube is a self-hosted version of the same thing, which is also has a free option to run. SonarLint was the extension I was running inside VS Code, which points out a whole bunch of issues, including the extra one that I hadn't fixed, but cognitive complexity as well, showing you all the positions in which you are adding complexity to a function. ESLint, of course, is brilliant, as well as our open source linter to tell us stuff like this. It will definitely tell you about the other 4 issues, but doesn't have an idea of cognitive complexity. However, at Sonar, we also produce the ESLint plugin Sonar.js, which has cognitive complexity as well as a bunch of other rules that we like using included in it. And so if you do want to, if you're already using ESLint and you want to check for that cognitive complexity within your code, then ESLint plugin Sonar.js is a good thing. I've got some of the links. There is a QR code on the final slide of this, which you'll be able to get these from. They link to the cognitive complexity paper. I'm not normally one for reading computer science papers, but I've read this one more than once now, and it's actually quite a delight to read and very understandable. It is mostly written around Java, although there are appendices for JavaScript, and it makes a lot of sense. That's another link to Raymond Chen's post about designing for readability. There's a link there to all of the JavaScript rules that we look at in Sonar. And there's also a link if you ever want to write a Reveal.js presentation that throws confetti on screen. The plugin is also available on my GitHub as Reveal.js confetti. So otherwise, like I said, I think aiming for clean code, aiming for code that we can understand and maintain easier and run better in production is a good target. But like I said, I'm not saying, hey, go fix all the issues right now. If your application is running, it's running. Just clean things up as you go. Refactor things as you find them. And particularly the complexity. If you can fix the complexity of functions as you find them, you will leave your code base in a better place for the next person, and that next person could even be you. Refactor those complex functions, that is something worth thinking about. Thinking about code for readability, code for yourself, code for your colleagues, code for your team, and code for the people that will be maintaining the code long after you're gone. and then code for your future self. Like, keep yourself in mind, because if you have to answer things about your code and you have to read it again, then it's always important to be able to understand what it's doing. So that's it. Again, my name's Nash. I'm a developer advocate for Sonar. It's been an absolute pleasure to speak to you here at Malmo. That QR code will bring you up the slides in your browser, and it will also do all the confetti as well as you get to the slides that have them. Otherwise, thank you so much for coming this morning. Thank you.